So welcome to the first video in a series that's going to look at integration. So in these videos we're going to look at both indefinite and definite integrals, and the difference there is one of these integrals, the definite integral, has limits or terminals as part of the integration. And in this video, the first video in the series, we're going to look in particular at the integration of polynomial functions. And we've got a formula here that says when we perform the integral or antiderive x to the power of n with respect to x, we get 1 divided by n plus 1, which is the new power, once we've added 1 to that power, times x to the power of n plus 1, which is that process of adding to the power. So you might be able to see there that that's the opposite of differentiating, where we would have taken the power at the front and subtracted 1 off it. We now add 1 to the power and divide by that new power. And we get this plus c here, which is a constant of integration. And that takes into consideration any vertical translations that are lost when we perform differentiation. So we've got to remember to put a plus c on the end of our expressions here. And this rule is going to apply for all powers where n is not equal to -1. And we'll see in a later video how we deal with powers that are -1. So our first example is an example of an indefinite integral. So that's where we don't have any terminals. So we want to integrate 6x squared plus 5x minus 4 with respect to x. So applying our formula, this is going to equal, and we have 6x, and we add 1 to the power, so that'll become 6x cubed. And then we divide by the new power, which is 3. So again, we're just applying this rule over here. And then we're still going to have plus 5x, but now when we add 1 to that power, this was a power of 1. We're now going to have 5x squared, and we divide by the new power, which is 2. And then when we have a constant like minus 4, we simply introduce the variable x, and we get a plus c value here. So if we just simplify that slightly, 6x cubed over 3 is simply 2x cubed, and then plus 5x squared over 2 can't be simplified, so we leave that as 5x squared divided by 2 minus 4x plus c. So that's the answer to the first part of the question. So the second part we're going to look at now, we go from having an indefinite integral to a definite integral, and that's where we have terminals, which are 3 and 1. So to evaluate this, the first thing we're going to do is we're going to find the antiderivative. So we're going to do essentially the same process here, but you won't need to add the plus c on this time. So when we have minus x to the power of 3, that becomes negative x to the power of 4 divided by the new power of 4. And then we have plus 3x squared here, which becomes plus 3x cubed divided by 3, which is simply x cubed. So we're going to evaluate that antiderivative between the terminals of 1 and 3. And they were the terminals that were supplied at the start of this question. So we have a theorem that allows us to evaluate this. And that says that what we're going to do is we're going to take the antiderivative, which we might represent as capital F, and we're going to evaluate that at the upper terminal, in this case 3. And then we're going to take the antiderivative evaluated at the lower terminal of 1 away from that. And just a reminder that symbolically we're just representing this antiderivative as capital F of x, just so we can keep track of what's going on there. So when we do that, this is going to equal, and substituting 3 in, we're going to have minus 3 to the power of 4, all divided by 4, plus, and then we're going to have 3 to the power of 3. And then we subtract away from that 1 substituted into the antiderivative, which is going to be minus 1 to the power of 4 divided by 4. And then we're still going to have plus 1 cubed inside that bracket. And now our job is just to simplify that. So this is going to equal, and we have negative, and then 3 to the power of 4 is 3, 9, 27, 81. So we're going to have minus 81 over 4. And then we're going to add on to that 3 cubed, which is 27. And now just be careful with this negative here. We can't forget about it. So 1 to the power of 4 is just 1, so we're going to have minus minus a quarter, which is plus 1/4. And then we're still going to have this plus 1 cubed, but the negative here is going to make it a negative. So we're going to have subtract 1, and that's the second bracket subtracted away. And now we're getting quite close to our answer now. So we're going to have minus 81 over 4 plus 1 over 4, which gives minus 80 over 4, which is negative 20. And then we add 27 and subtract 1, and that is going to equal negative 21 plus 27 gives 6. So that's the value for that definite integral. And now if we wanted to, we could represent that value graphically. So there's a relationship between a definite integral and the graph of a function. So if I quickly graph this, so we've got a graph of it. And if we go between 1 and 3 for our definite integral, that's the same as going from 1 to 3. And what we actually calculate is we get that this would give the area under the curve. Now, I do have to mention that that is only considered the area because the curve is always above the x-axis. And in other videos, we'll delve into what happens when the areas go below the x-axis, or even what happens when you have a mixed set of areas. But for this one, the problem goes from 1 to 3. That graph is always above the x-axis or equal to it. So the area is equal to this integral that we just found, which is 6. So that area there is 6 units squared. So if you want to see more information or more examples of how to evaluate problems like this, make sure you click on the links that are in the video just below. And stay tuned for the second video where we're going to look at integration of power functions.